Sorry about that. There are times when my webcam is flaky. All right. Hopefully that restarted everything and my webcam actually is doing what it's supposed to now. I'll give everybody a couple minutes to get all logged back in. Anybody else have lab questions then that either my people or other people's labs?
You said our lab is, are we meeting Monday or we're not?
Yes, Monday the 7th.
Okay.
Yeah, same bat time, same bat channel. So 5:30 on Monday, just it's Zoom.
Okay.
Because it's the final lab of the semester and the college decided that they didn't want any students on campus for the post-Thanksgiving couple of weeks because everybody's nail chewing about how possibly contagious people may or may not be. So given the state of the news on things like CNN and MSNBC, it's all kind of
So are we going back like the 11th? Like we're going?
No. There are no more face-to-face meetings for lab. We are done with the physical portion of lab for the semester.
All right.
So yeah, if you have, especially everybody who has me for lab, I think I went through and activated the ability to submit through Canvas for all of the assignments so that anything you still owe me can be submitted up until midnight on the 14th so that I can grade it, because the 15th is when I have to report everybody who has somebody different for lecture. I have to send lab grades to them. And also I have to finish out lab grades to integrate with lecture grades for everybody who has me for lab also. It's slightly more complicated than usual. I mean, yeah, we always have to do the integration part because there's always a number of students who have a different professor for lecture than they have for lab. So there's always a certain amount of swapping going on. So we always try to cut off lab turn-ins a couple of days before final exams, because it takes time to get stuff graded. And grading stuff digitally is one more level of complication. All right, so I think everybody I accidentally sort of kicked off when I had to restart my webcam, I think is logged back in. All right, we're going to dig back into some more molecular geometry. And the last thing that we were talking about on Tuesday was, okay, we did the linear one, which is the one here that has a single molecule in the center and one leg on each side. We also talked a little bit about the trigonal planar one. This is the one that is flat and has 3 legs, but no additional electrons. And then we kind of mentioned the tetrahedral one, and that was kind of where I left off on Tuesday. So let's take a look at the pictures here, and then I'll show you my Tinker Toy build for the tetrahedral one. Methane really is the molecule that probably gets picked on the most often when you're talking about things that are tetrahedral, because it's a nice small molecule that has identical legs, because all of the things that are attached to the carbon are hydrogens. And it's tempting from a, oh, well, if I'm going to draw it, I can just make it look like a plus sign, okay, which is fine from the drawing things out point of view. However, when we talk about this from the actual physical, how it looks in 3 dimensions point of view, then you have to really kind of embrace that z-axis idea. The idea that you have that third dimension available to you. So if you look at the thing that kind of almost looks like a little pyramid, it's a tetrahedron, okay, which in geometry is a 3-dimensional but 4-sided figure. Each side is triangular in shape. If you do D&D, as my kids do, and I have done in my life, there are 4-sided die. When you roll your 4-sided die, it is a little 4-sided thing as opposed to a more traditional die, which is 6-sided. And you can roll your 4-sided one, and it will tell you 1, 2, 3, 4 as your options instead of 1 through 6. Looking at the bond angle also is a piece of this puzzle. Note, the bond angle is not 90 degrees. 90 degrees only works if you're in 2 dimensions for 4 legs. Here we have 109.5 degrees, which sounds like a really weird number. It is, however, what it works out to be when you take spherical geometry and you slice it in 4 directions. All right, so let me show you my little 3-dimensional one here. We kind of looked at this really briefly on Tuesday. So we've got one that appears to poke straight up, and it kind of looks like I have 3 legs that are all poking downward. But remember, I said this is a symmetrical molecule. So if I rotate it, okay, and put like this one on the top, it actually looks like it's still the same molecule. This is where that whole 109.5 comes into play. If you kind of look at the angle here, it's an obtuse angle, so more than 90 degrees, which kind of gives you a different visual when you're looking at it on the 3D rendering of it. All right, so that's AB4 in terms of its Vsepar formula. Now let's add another one. Okay, AB5. Now this one has a 2-word designation for the name. It is known as trigonal bipyramidal. Okay, think about what it kind of what those words are telling you. So part of it is triangular, but if you took 2 of those 4-sided pyramids and you stuck them bottom to bottom, this is why they call it bipyramidal. If you look at it in its structure, it also is one that does not have all identical angles. Some of the angles are 90 degrees, and some of the angles are 120 because of the way the molecule is put together. Again, we're trying to embrace how far apart can we manage to get 5 legs in 3-dimensional space. And we're also embracing the idea of mixtures of S and P orbitals, which eventually we will get around at the end of this chapter to talking about in terms of hybridization. All right, more Tinker Toys. All right, so here's my 5-legged one. So if I have it sitting right side up, okay, I can kind of spin it and look at the fact that one is poking downward and one is poking upward. And then I've got these 3 that are rotating. Whereas if I kind of look at it end on, and it looks like a little spaceship, then the straight one is poking outward and the other one is poking back toward me. And you have these 3 that are all of the ones that have the 120-degree angles going on. So it definitely is kind of an odd looking little thing, kind of looks like a space station, because of the fact that you have the rotating part, but then you have one up and you have one down. All right, there is one last variation that allows you to do 6 legs. All right, this one goes by the name of AB6 in terms of its Vsepar formula. And its word is octahedral. And this is weirdly deceptive, okay? Because we know oct from our prefixes that we used in nomenclature. Oh, oct means 8. But part of the idea here is that it's not 8 legs, not like a little octopus, okay? It's 8 sides. If you took 2 4-sided pyramids and stuck them bottom to bottom, you end up with an octahedron, something that actually has 4 sides on the top half and 4 sides on the bottom half, so 8 sides altogether. But this also allows us to go back to the idea of having the same bond angle everywhere. Unlike the trigonal bipyramidal one, which has the 2 different angles, this one goes back to having them all be 90 degrees apart. So there is a certain level of simplicity in that part. All right. So here's my little octahedral one, okay? So, and if I tip it a little bit so you can see all the legs a little bit better. We've got the one poking upward. We've got the one poking downward. But then the 4 that are orbiting are all also spread equal at 90 degrees. So even if I kind of tipped it in a different direction, this is a little bit more like the tetrahedral one of, since all of the bond angles are the same, it doesn't really have like a right side up and an upside down the way that the trigonal bipyramidal one kind of sort of does. All of those are the ones that have no lone pairs. So now we have to start in the direction of those that do have lone pairs. And I'm going to pick on the one that is designated AB2E. Now this time, since we have an E, the E represents a pair of electrons, because remember, we're always doing it in pairs, a pair of electrons that are not part of a bond. So when we're looking here at my SO2 molecule, and ooh, resonance again, this gives us a situation where, since sulfur often likes to have just 2 bonds, we can force it to have 3 bonds. Note, this kind of gives me a positive on one end where the sulfur is and a negative on where one of the oxygens is. But like a little windshield wiper, it is going to swing back and forth, and I only gave you one of the resonance forms here. The E is the two dots that are sitting on top of my sulfur. Now, one of the things that makes molecules that have lone pairs different. Lone pairs are fluffy. Lone pairs take up more space than bonded pairs, but then they also exert pressure on the bonds. So instead of having a linear molecule, instead of having my two oxygens sort of flex out to the side and having it have a bond angle of 180 degrees, I actually only have kind of a bent molecule out of this. And actually, I probably should have put in parentheses here. You will also see this referred to as V-shaped, okay? V-shaped, and again, we have a slight discrepancy on what you may see referred to as your bond angles. Some textbooks will claim that your bond angle there, instead of 109.5, is a little bit less, about 107. You also might run across a few textbooks that will say that there's supposed to be about 105 degree bond angle there. So a little bit less as a general trend than what we're seeing for things that were tetrahedral. All right. I have a particular reason why I bought a specific Tinker Toy set, because this particular set comes with these, okay? And if I rotate it around so you can see, it's kind of flat, okay? Looks like a ping pong paddle for Barbie. But in fact, they are a lone pair. They represent a non-bonded pair of electrons. If I rotate it so you can see my double bond a little bit better. So my sulfur's in the middle. I have two curvy pieces here that are my double bond. And then I have the other oxygen over here on the other side. Okay. But especially because of the curve, the spread curve of my lone pair, it helps to make it a little bit more obvious that the lone pair is kind of exerting a spreading effect above the atom, which then kind of squishes the legs of the atom, or of the molecule rather, a little bit closer together than they might otherwise be. So think about that in terms of how all of this kind of fits together. All right. AB3E. So it has 3 legs, except one of those legs, has 3 legs, but the fourth, we'll call it a bonding area, is a lone pair. And again, this one I found a picture that had the label of 107 degrees in it, so that you can kind of see the idea here of we've got 3 legs that are pointing down, kind of like a camera tripod. And then you have that empty space up on top, except it's not truly empty. Now, beware, okay? The name sounds super similar to the ones we just covered. It's not trigonal bipyramidal. This time we're taking out the B and the I. We're going to call it trigonal pyramidal. It's a little three-legged pyramid. Okay. So I took my tetrahedral molecule, which had a leg poking out the top, and I removed it and I put this lone pair in its place, which then kind of reinforces the idea that all of these legs are kind of sitting, poking downward at a little bit of an angle. And then you have this empty space, which is not literally empty, up on top where your lone pair is. Lone pairs are a powerful force in terms of how you are viewing the geometry of your molecules. All right, now we get to a weird one. If you had the 5 areas that we were looking at previously, and you took one of the legs off, you made it a lone pair instead. Now note, there's 2 different names here, and either one is fine. Textbooks disagree slightly. One term the textbooks use is to call it a seesaw, because it kind of sort of looks like a seesaw. It has the 2 legs in the middle, but they're at kind of an angle. And then it has the 2 seats, one on each end, such that if you built the molecule, it does rock back and forth a little bit if you put it on a flat surface. But it has that lone pair. Now look at the slightly right-hand picture there. It has a circle around where your lone pair is to kind of give it a little bit more emphasis on showing you where it is. You also, and we'll run across things that will tell you less than 120. A lot of times they're really generic about how they label the bond angles for this particular molecule, because part of it was up and down, part of it was at 90 degrees, but then you had the part that was at 120 degrees. Well, once you put that fluffy lone pair in, everything gets contorted just a little bit, which is also why they call it distorted tetrahedral. So all we can really say, and actually your lab book supports this idea, is they will often just say less than 120 as a way to describe the bond angles for this. So here's my little molecule. Let me grab my notepad up here so I can kind of show you how it rocks back and forth. It's like, this is kind of why it's referred to as seesaw, because if I have the 2 legs pointing downward, it actually is kind of tippy. It can go back and forth. And then, oh crap, and I did it again. It's not going to let me start my video. Phooey. Okay, this is making me crazy. And then it claims it can't detect my camera. There. Okay. So anyway, lone pair. Okay. The lone pair squashing downward on all of the legs. This is definitely one of the weirder ones, okay? It's also somewhat less common. I won't call it uncommon, it's just less common than some of the other ones that we have looked at. All right. What if you had more than one lone pair? Okay. Water molecules are very much the absolutely stereotypical version that has AB2E2. So not only do you have one lone pair, kind of like the SO2 molecule, you've actually got two lone pairs. And we talked about this a little bit in passing back when we did the chapter with all the precipitation reactions in it, because we talked about aqueous situations. And we talked a little bit about the fact that water is polar, that lots of the negativeness are kind of at the pointy end of the molecule. And so by looking at this molecule, and like I said, there's a little bit of also iffiness about this one. Some textbooks will go, the bond angle is 104.5. And some of the other textbooks will claim it's 105. So right about in that area. All right, here's my water molecule. Okay, it kind of looks like a bizarre butterfly, especially because I've got my two little lone pairs here. I can make it look like Mickey Mouse. Two legs. Okay, these are my hydrogens. But because my lone pairs are all concentrated on one side of the molecule, this is really and truly what drives the fact that it is a polar molecule. We will actually come back to polarity of molecules more probably Tuesday. I don't know that I will get to that today. That's one of that and hybridization are like the last couple of things of the chapter. So here's your water molecule. All right, now we do get into one of the truly kind of weird ones. They refer to this as the T-shaped molecule. So it has 5 portions to it, portions that are available for legs or lone pairs, but only 3 of them are actually occupied. And so this goes back to that whole 90 versus 120 thing. But if you take off 2 of the legs and replace them with lone pairs, we still kind of get 90 degrees between the point up one and the point down one and the one that's pointing off to the right-hand side there. But that left-hand portion is all kind of naked lone pairs. It does make it relatively T-shaped. So AB3, 3 legs, E2, 2 lone pairs. Okay, so here's my little butterfly wings, okay? And then if I turn it this direction, you can really kind of see the fact that it's T-shaped because this part is straight across, and then I have the one leg that actually contains a bond pointing straight downward, and I have all the negativity on my lone pairs that are kind of spread out on one side of the molecule. There's not a lot of T-shaped molecules. It definitely falls in the category of less common, borderline rare. Then we hit the linear one. Now we kind of go from less common to there's only actually a very few molecules that do this. You actually get a linear molecule out of it. Note, I flip-flopped my numbers. Now I've got AB2, E3. All of the lone pairs orbit the middle, such that the bonded pairs poke up and one down, or one left and one right, depending upon how you're holding the molecule. This is a way to get a linear molecule, but it's a weird and uncommon way to get a linear molecule. Doesn't happen a whole lot. In fact, the one that's printed here is one of only a small handful of molecules that actually do this. This is known as triiodide. If you are somebody who is taking 112 as a later class, triiodide is something that we use in a particular lab. So here's my weird linear molecule. We've got this one all the way straight across to that one. And then we've got all these lone pairs, okay? If I show it a little bit more like this way, okay, we can kind of see all of the lone pairs are orbiting, kind of like little planets. But you have these two that are in opposite directions. And that's where you get your linearity. Now we get back to one that's a little bit more common. However, more common is relative. Square pyramidal. You, instead of having 6 legs, which gives you octahedral, this one has 1 lone pair on the bromine. Note, my bromine violated its octet, also known as an expanded octet, because it has 5 bonds plus a lone pair. So that's definitely more than 8 electrons. If you stick a large halogen, and you can actually kind of see this as a methodology from both the molecule above there, the triiodide molecule, it has more than 8. If you put bromine in the middle, you can convince a molecule to have more than 8, more than your octet on the center atom. This one's AB5E. Back to 2-word names. Square pyramidal. If you took off the lone pair and you let it sit down flat, you would see that it kind of looks like pyramids of Giza. But that lone pair is kind of an empty spot. So I'm going to cover up my lone pair for a second. Okay, so if you kind of look at this without the lone pair showing, you see the 4 legs that are spread out at 90 degrees. You see the one poking upward. There's my lone pair. The lone pair is sort of isolated on one side of the molecule. It makes it a little bit lopsided because like everything is over here and then there's this naked space that has just electrons on the back end of the molecule. It definitely has kind of a lopsidedness factor to it. What if I took off one more? Okay. Remember I told you before, now and again, you can coerce a noble gas, but only the big ones, not helium and not neon. Argon is a dicey perspective. Krypton and xenon, though, are more likely to cooperate if you do certain things to coerce them. This one is square planar. So we have AB4, 4 legs, E2. But this one is odd in its own right, in that, unlike many of the other molecules we've looked at, where the electrons that are lone pairs tend to blob over on one side of the molecule, this one spreads them apart. This one puts one of the lone pairs sitting on top and one of the lone pairs sitting on the bottom. This is how you get the square pyramidal geometry out of that. So if I look at it from the end Okay, here's my lone pair. If I kind of tilt it a little bit, there's my lone pair in the back. But you can kind of see they make a square. If I sit it right side up like this, you can kind of see that there's my lone pair up on the top. Okay, here's my lone pair on the bottom. And all of the four legs are all 90 degrees apart on the same plane. Because if I kind of like hold it exactly right, you kind of don't see the back one at all. All of this stuff really, truly kind of requires you to embrace the idea of 3 dimensions. So obviously, I don't really expect you to own a Tinker Toy set like I do. You can fake it if you want to build your own with toothpicks and marshmallows, or toothpicks and gumdrops. Even if you happen to have, kids and they have Connects, which are kind of a 3-dimensional Tinker Toy-ish toy, you could build yourself some molecules to look at if you think that that's helpful. So some things to keep in mind. When you are trying to decide your molecular geometry, drawing yourself out the Lewis structure with all its accompanying dots and legs, straight lines, is actually a really big tool. You are paying the most attention to the middle atom. The middle atom is the controller. It's the one that, if there are lone pairs, it makes a difference. Count up your bonding pairs, count up your lone pairs. That helps you figure out your Vesepra formula, which in turn helps you correspond it to the 1 or 2 words that are your geometry. So I have a couple of examples here. If we look at PCl3, so phosphorus has 5 electrons. Each chlorine brings 7 with it. So as you begin to set this up with the phosphorus atom in the middle, you need 1 leg for each of the chlorines, kind of keeping in mind that chlorines, halogens in general, mostly only want 1 bond. Phosphorus, which is under nitrogen, generally likes 3 bonds. So once you kind of get that all together and you put all of the lone pairs around your chlorine, so 2, 4, 6, around each of the Cls, and then you would discover you have 2 left over, and they go with the phosphorus. So in terms of my Vesepra formula, I've got AB3E. A lone pair on the phosphorus is my E. And that makes this a trigonal pyramidal molecule. What if they weren't all the same? Doesn't actually make a super big difference in terms of the geometry. CH3Cl. So I've got 3 legs that are identical, but 1 that's different. I've got a carbon atom in the middle, and carbon is always super unhappy if it doesn't have 4 bonds. So 1 to each of the 3 hydrogens, 1 to the chlorine. Chlorine has more valence electrons, so we're going to try to make sure it's happy with an octet. By the time you fill up that octet on the chlorine, there aren't any leftovers. So there aren't any E's in your Vesepra formula. You have AB4. Yes, one of them is a different atom, but it's still AB4. And this makes it a tetrahedral molecule. What if you did have leftovers? So tellurium is not one we see a huge amount of, but it will function as a center atom. When you look up tellurium, it is down near the bottom of the column that contains oxygen. So it has 6 electrons. Each of the chlorines each brought 7. So we have quite a few electrons to deal with here. By the time we start spreading them around, you put the appropriate number, 8 total, 1 bond, 3 pairs of dots around each chlorine, you actually discover there's 2 that you didn't use yet. So they get put on the center one. So in this case, we've got AB4E. And you can call it either seesaw or you can call it distorted tetrahedral. Either word is fine. All right, so that's all of the basics for the geometry itself. We're not done yet. This is a big picture kind of thing.
May I ask a quick question?
Yes.
Unfortunately, it's probably a little bit off topic. But when these molecules form, do they form in these geometries, or do they like bond and then shift to where they fit the best?
No, they form this way.
Okay. So is there any sort of like, oh no, there's not an oxygen on that side, so it doesn't happen? Or is it just sort of like magnetism and forces where it puts the oxygen where it wants and then forms the bond?
Okay, the thing we haven't got to yet, which is at the end of the chapter here, is called hybridization. All those things we saw back when we did electronic configuration, remember, sometimes we had lone electrons and sometimes we didn't have lone electrons. Sometimes we had one up and one down. If you don't have lone electrons, you can't make a bond. So if you are making a molecule, it smushes all bits of S's, N, P's, and D's into different shapes, which allow you to create a molecule.
Okay.
And then because you've done this sort of stuff to your S's, N, P's, and D's, that is actually the underlying reason why they become certain shapes as they are forming.
So like the one with that has like the donut in the middle, if you have the lone pair still on each end, you're looking at planar geometries. Whereas if you have like 4 balloons, you're looking more like a tetrahedral.
Yes and no.
Okay.
Because the hybridization borrows things from more than one layer sometimes.
Okay.
Or more than one shape in the same layer. Let's put it that's probably actually more truthful. You could have 3S and 3P and you smush them together and you get things that kind of look like a mixture of both.
Okay.
We're getting there. It's
All
coming.
right. Thank you.
So at the beginning of the chapter, we talked about polarity of just a bond. Okay, one atom at each end, and all we were really paying attention to was things like electronegativity. Well, that works fine if you only have 2 atoms. But what if you have a molecule that has 3 or 4 or 5 or 6 or 7 or 8 molecules? Actually, I guess not 8. You could have 7. You could have 6 legs and 1 in the middle. what about the molecule as a whole? So let me pick on carbon tetrachloride. So several different pieces of the puzzle kind of fit together here. If you look at just one bond, if you look at just carbon bonded to one chlorine, so that particular bond, just one, is polar, because on the periodic table, the chlorine atom is way closer to the fluorine, and fluorine is the king of electronegativity. Carbon's a little bit further away, so it's a little bit less electronegative. Remember the little squiggles that look like an unfinished number 8 stand for the word partial. So we have partially positive down near the carbon and partially negative out near the chlorine. But I have this perfect tug of war. Okay, think about it this way. What if you took 2 chains and you took 4 cars with the exact same engine and they're the exact same model car, so they all weigh the same, and you revved them up, and then you looked at the spot where the 2 chains cross in the middle? Nothing happens. It's the perfect tug of war. So even though each bond is polar, if you pull exactly and equal in opposite directions, you get a non-polar molecule. So carbon tetrachloride, even though it has 4 somewhat polar bonds, is actually a non-polar molecule. Carbon tetrachloride is a molecule that can be used for dissolving things like grease. Not that you would want to, it's carcinogenic, but on theory, okay. Because it is non-polar, it will dissolve things that are greasy. We'll refer to them as hydrophobic. Not a word that we see a whole lot this semester, but pops up next semester again. The other thing that we need to consider is, remember I said things with lone pairs? Lone pairs make a huge difference. So now we return to the water molecule. And as a chemist, walking down the aisle in the grocery store where they sell all the bottled water, and there's a brand labeled Polar, which I know from a branding and a marketing point of view is supposed to make you think, ooh, like the North Pole. But because I'm a chemist, my brain goes, of course water is polar. Because look at your molecule here. Your pointy end, where the 2 lone pairs are, is kind of where all the negativeness of the molecule is located. And the legs where the hydrogen is are more positive. So yeah, you could bisect it in one direction and kind of say it was symmetrical, but if you bisect it in the opposite direction, then it's definitely not symmetrical, because you have 2 legs on one side of the mirror and 4 dots on the other side of the plane. Yeah, water is polar. One of the things we kind of sort of mentioned a little bit in terms of precipitation and things like that is water's polarity is what allows certain ionic salts to fall apart easily, whereas others are much less soluble. So you can have polar bonds in a non-polar molecule, but if everything is symmetrical, the molecule might be non-polar. But if you can cut your molecule in one direction, that leaves all of your electrons kind of sitting off on one side, then you end up with a polar molecule. So as a general statement, okay, we can probably say things with lone pairs on the center are mostly polar. There's one or two exceptions, but we can make some kind of generalizations out of that. That leaves us hybridization and multi-bonds to cover on Tuesday, and then you'll have everything you need. So over the weekend, I would say begin to work on your homework set. You should be able to draw Lewis structures at this point. You should be able to figure out how many bonds, how many lone pairs. You should be able to figure out your Vesepar formula, and that will help you with your molecular geometry. And then we've sort of covered polarity. We have not done hybridization yet. That as well as multi-bonds is the last kind of lump here at the end of the chapter, but we're kind of nearing the bitter end here. Questions about stuff from the past couple of lectures? Anything that has to do with this chapter?
I got a question.
Yes.
When we join these up, and some of these got angles, right? Like you got like 45, you got like 120 and 90. We don't have to be exact. I'm saying as we join these.
Oh no! If you're drawing them, I don't care. What I'm looking for is that you have the correct number of straight lines and that you have the correct number of dots with the given atoms. If you draw them such that the angles are a little different, that's fine. Lewis structures are often squashed. You know how like when you do geography, there's the Mercator projection thing where they take the globe and they squash it flat so that things aren't actually as far apart as they are in real life. That's kind of how Lewis structures versus molecular geometry looks like. When you draw it in 2 dimensions, you've kind of flattened everything anyway, so you may not have what looks like appropriate angles. I'm just looking for lines for bonds and dots for lone pairs. If your angles are a little iffy, that's fine.
Okay. And one more question, right? And when say like we drawing our lines and we drawing our bonds, each one of those ends accounts. Each one of those lines is basically 2 because you got
yes.
I'm doing a circle.
Yes. Okay. Lines are 2. The dots are 1 each, basically. But if you look through the examples that are in my notes, but also the examples that are in the textbook, dots for general chemistry purposes are always drawn as like a pair. Okay. All bets are off if you get to organic, but for general chemistry, we are treating electrons as if they only travel with a buddy.
Okay. All right.
Other questions for this or for lab stuff?
I have a quick question.
Yes.
For the homework, do you care which letters we use for the Vesepar?
Oh, no, that's fine. Like I said, your textbook does not agree with your lab book. Your textbook, I believe, sticks with the AB designation, but I believe your lab book does AXE. As long as you're consistent, I can tell.
Awesome. Thank you.
So if you have me for lab will be Zoomed on Monday at 5:30. I'll talk about all kind of go back through a lot of these pieces that we've already covered again. And then you have a week to finish up that last final lab. But keep in mind, your end goal, because we are getting very close to the end goal, is everything has got to be submitted via Canvas by the 14th, because it will like after the 14th, I've got to start totaling grades. So spend some time this weekend if you have stuff you still owe me. And then hopefully that'll only leave you with one lab left to do in the final week prior to the exam and the fourth test. I have it scheduled right at the moment. So the fourth test should be Friday to Monday, but then you only have 2 days to do the final exam. You basically have, well, 2.5 days. Okay. You have Tuesday, Wednesday, Thursday for the exam. And then I have to submit grades because I have to submit grades on Friday. And I haven't finished typing the final exam yet. I'll talk about that more later. But the final exam is all multiple choice, but it is 50 questions. I'm fighting with the Canvas system.
Then
But
the final exam is all cumulative, right? It's like every chapter?
yes,
Okay.
yes, it will cover all chapters. I tried to be relatively equal so that each chapter is, since we did 8 chapters and there's 50 questions, that's 5 or 6 questions per chapter. I tried to make it a relatively equal spread so that it didn't focus on any one particular chapter because we spent all semester doing this.
Will the questions be similar to ones on our?
They will be
chapter test?
similar. They will not be identical, but they will be similar.
So studying those instead of
Yes,
just going straight to the
yes.
book
I
is-
would say, well, does Canvas let you go back and look at the tests later?
only through Respondus.
Yeah.
browser, but
Okay,
You have to be in
Okay.
the browse in the lockdown system to look at it.
okay. But also look at your homework, okay? Because the homework has always been a really key function of what the important parts are in each individual chapter. So there's answer keys, remember, to all the homework, and I'll get around to posting the final answer key after we get done with the chapter. And so look at homework too as a way to kind of prepare for the test. And since it's going to be the same criteria, it's going to be, open textbook, open note. You can use your lab book if you want, just not each other and not the internet. So if you think you can make yourself a note sheet if you want of these are the things that I think I'm going to need, like right at my fingertips. That might be an easy way to kind of help you organize your thoughts for this type of a final exam.
And it's still 4 hours, like for the
No,
final
I will
exam?
probably do 6 hours for the final exam
Oh, okay. Ooh, that's a long time.
because there's more questions. So I will probably give a longer time frame. I
Okay.
haven't, like I said, I haven't quite finished typing it yet, but I'm getting there. I have 74 out of the 100 points done so far. They're all equal. They're all just 2 points apiece. But yeah, Canvas is an almighty pain in the ass to like type things that have, because like think about it, Greek symbols, okay, and subscripts and upscripts and math and yeah, typing in Canvas is much more of a pain than just typing in Word. Because Word, I can just have a toolbar and just like, click up and down on things. Yeah, it's just not that simple on Canvas. All right, so on Tuesday, we will finish the last little bit, which basically is hybridization and multi-bonds. And then on Thursday, it'll be go over homework, answer any final questions so that you can have all weekend to take that fourth test. Also probably talk a little bit more about the exam. By then I'll be done typing the exam. So I'll probably also talk more about the exam. Tuesday the 15th. There's nothing new, obviously, going to be covered. I'll be online that night for question and answers if people have stuff that they want to ask prior to them taking the final exam. So just kind of pencil that in as you don't have to show up. But if you want to, that way I can answer some questions in real time if you have stuff about the final that you want to check on. Otherwise, I will see you on Tuesday.
See ya.